conductive, which could enable quick solidification of the metal, and at the same time it should withstand that kind of a heat and the wear that happens in the material. So I'll go into details of this, but the interface between the metal, the liquid metal, and the uh, chillvent is normally the H13 or H11, which also we use some of the copper-based materials here, which are composite with this kind of a H13 initially. Then we have the short sleeve. Again, the short sleeve has an interaction with the hot liquid metal, and then it needs to be highly erosion resistant, so higher hardness than the basic insert material. So hardness around 50 to 55 is normally done on this material. So to attain this kind of hardness, we have a plasma ion nitriding or any of the coatings that are. So this is where the coatings come into play, where you need to enhance the surface uh, properties or surface modifications have to be done on the tool steel. Uh, I request if anybody wants to stop me and ask me anywhere in between, you're welcome to do so. So here within the short sleeve, we have a plunger, a tip and a plunger rod. So we have different kinds of plunger tips and plunger rods which are used. A Copromac with a steel ring is one which is used recently, but then the age-old mechanized cast iron material is used. And again, this is to inject the liquid metal with a high velocity and pressure and to cool the biscuit fastly. Sorry for the spelling. So this needs to cool the biscuit very fast. So you need to have a high conductivity. You have a water cooling arrangement. So corrosion resistance and all these things need to be built into the material requirement. So this is where different kinds of materials come in. And with respect to the plunger tip, there are different kinds of designs that come in where we have different materials that go into it. Like we have the 440C ring that is put onto this kind of a plunger tip with copper, and different kinds of different modules are available. I'll not go into the details of the design of each of these, but then dwell upon the material requirements. Now the ejector pins, these need to be very rigid because you can see in the figure here, in the picture here, the kind of length that are involved before their application and the kind of buckling that can come in. So we have to have good kind of rigidity in these pins. So basically to reduce the breakage and to avoid any of the casting catch up and to reduce the warpage in the casting. So we have these ejector pins in the die, and normally the ejector pins are again the kind of uh, materials that go up to 40 to 50 RC. So the cooling system, the water cooling system is used basically to remove the heat from the die. So all the materials used in the water cooling system need to be highly corrosion resistant, at the same time good thermal conductivity, so that the heat can be easily removed, which basically the functions are to remove the heat and improve the solidification, to improve productivity. The list is out here. So the materials that are normally used are stainless steel. and copper tubes are used here so that we have good conductivity in the cooling systems. And different kinds of cooling systems are listed out here. And for all these, you have multi-material kind of situation where we have some of the cooling systems. I'll be going into the details where they are cladded copper inserts to aluminum and diffusion bond cooling, jet cooling systems and things like that. Again, as I said earlier, the different kinds of cooling systems are here. So you have the nozzles, which are made of copper and different kinds of materials. The stainless steel nozzles are also made. And this is the different options that are available based on the kind of a requirement in the cooling. At the same time, we could also look at modifications in the inserts, which actually help in enhancing the cooling. Like what I said here, we have something like conformal cooling in this, where the additive manufacturing and different kinds of materials, powder materials are used here in additive manufacturing so that you could actually enhance the cooling in a spiral way. So you have a spiral cooling in the insert, which actually enhances the cooling and controls the solidification. So here, as we can summarize at this stage, we talked about copper, we talked about H13 steels, we talked about cast irons, we talked about uh, powder metallurgy, and we talked about multi-material diffusion bonding. We talked about the surface preparation in terms of nitriding, plasma nitriding. So this is the kind of variety of materials and processes that are used in the dies, and these could be tailored based on the requirements. And as I said, going forward in die casting, it appears that the complexity of the component design is changing so much, and it is becoming more and more demanding in terms of enhancing the properties of the uh, castings in terms of the mechanical properties that are required. For example, we have this the properties of the castings need to be increased in terms of the ductility. So iron content is something what we need to control much below the uh, conventional alloys. So that is where it this kind of a design in the die and the material selection plays a role, where we need to give that kind of extra mile to the interaction of the alloy that is cast and the die casting tool. Because conventionally we have much higher iron content in the uh, aluminum alloy, which actually enables pressure die casting process to uh, be easy without any of the sticking of the metal to the die, and easy ejection. And soldering is something which can be avoided with higher iron in the liquid metal. So because of the requirements of the application for higher ductility, alloys with low iron content are required for die casting. So this becomes a challenge. So what do we do in such cases? These are some of the things which we need to really work around so that we have a much higher solidification, so we do not give enough time for the phenomena of soldering. What happens when soldering happens? You have the kind of interaction, chemical interaction between the die surface and the liquid metal, and that is where soldering occurs. So once you have a much rapid solidification kind of a situation where you have fast heat extraction from the liquid metal, soldering can be avoided. So these are some of the things which we need to actually build into design and material selection, which enables such kind of complex requirements for the component are happening. So again, going forward on cooling systems, you have complex jet cooling systems. So very fine, thin jet cooling systems. So these require different kinds of material where you have much and the water cleanliness, especially in India, is not that good. So which interacts with the uh, material, and you have a lot of cooling channel blockages and things like that. So corrosion resistance becomes very important here in trying to select the kind of system. Now we have processes like vacuum. Again, to enable such kind of processes of vacuum, we we have to ensure that the liquid metal does not get into the vacuum system. So the best way to ensure that the liquid metal doesn't get into the vacuum system when the kind of vacuum is applied into the die casting machine, we have to select such that the vacuum valves, again, the vacuum valves have got different kinds of materials where you have a high thermal conductivity materials. So these are different areas where I'm just trying to enumerate the kind of different opportunities for different kinds of materials to get into the die for different applications and different requirements. So for the overflows again. So this is a typical example where you have to have a much higher thermal conductivity material uh, into the vacuum valve. So again, the guide pillars, the support blocks, these are all again are manufactured with different materials, and robustness of these materials are important. So in short, we have basic requirements for the cavity inserts, low thermal expansion. See, these are the materials which are actually embedded into a high toughness block of steel, and thermal expansion again. Thermal expansion again induces stresses into the system. So low thermal expansion is required, high thermal conductivity, which enables solidification, high temperature strength. So this material needs to withstand that kind of shock and that kind of a high temperature impact into the system, which is put into the insert or the die or any of the core. So they need to withstand this kind of a high temperatures shock or impact. So they require high temperature strength. Then it should not buckle, or it should not actually uh, uh, have a softening behavior at a higher temperature. Again, this is high creep strength. A lot of people keep asking me what is the difference between high temperature strength and high creep strength. Creep strength is something which is time dependent deformation here. So it should be stable. It should be having a good dimensional stability. That is where the creep strength comes into picture. It's high temperature strength is for that instantaneous high temperature, that kind of a strength for the material. But over a period of time, when with all this kind of cyclic temperatures up and down, the creep strength of the material should be very high and very good. So you have a thermal stability in the die. So this will actually help in getting good parts with good dimensional accuracy. At the same time, any kind of distortion in the die can be avoided. So over a period of time, you see that dies tend to flash. So it actually talks in terms of a poor creep strength of that material which has gone into it. And how to get all this on board, how to actually evaluate these materials, that is something which I'm going to talk about. And right from the genesis, what exactly these materials in terms of processes, what happens and why we need to insist on some of these uh, requirements on these materials. I'll be talking about that also. So it should have a high ductility. If you do not have high ductility in these materials, you can have a catastrophic failure of these inserts or the dies. So actually ductile material, it actually gives you early warnings before failure. So high ductility means a combination of high strength and high ductility is nothing but it's a combination. The product would be a high toughness steel. So if you have a good toughness in the material, so you have a combination of high strength and high ductility. So that is how it is described. So you have a tough material there on board. As I said earlier, again, corrosion resistance, erosion is again a basic virtue of a material that could qualify for a good tool steel, die steel for die casting. Before I go forward, any questions from the audience?
Hello, good afternoon, sir.
Yes, good afternoon.
This is Giridhar from Rane.
Yeah,
I'm taking care of time maintenance. I'm the in charge of that. I
yeah,
have a small question. You said that the soldering is something like iron content in the material also will be a reason for solving. So I just need some clarity over this, sir. How to select the materials with less iron and what is the material you wanted to suggest? So that because we have one product which we suffer with soldering, we are thinking that mass area where which is having weight reduction. That is the one area where we are repeatedly having soldering issue. So I
yeah.
just required some inputs.
Yeah. There are two aspects of this, Mr. Giri. The
Yes,
thing
sir.
is, here, one is soldering could happen because of high temperature, as you rightly said. You have a high thick mass, you have a high temperature there. Again,
Correct.
soldering could happen. Soldering is basically a phenomena where you have a chemical interaction between the tool steel and the liquid metal. So higher the
Sir?
temperature, sorry?
No, sir, no, sir. Please go on.
Yeah. So you have a higher temperature and the interaction between the tool steel, and that is why we use a lot of anti-soldering agents so that we form an interface between the liquid metal and the basic die. What I was trying to say is, in my presentation earlier, I was trying to say that the liquid metal what we are using today has got a iron content almost around 1%. And this 1% iron content is actually intentionally added into the liquid metal, avoid this kind of a soldering phenomena. So going forward, there'll be demand for parts that will require this high ductility in these parts that we are producing through die casting. So in such parts, iron content is expected to be much lower to enable the ductility in these parts. So that becomes a challenge when we design and select materials where when you have the in this case of yours, where you have a thick mass, you have the soldering. When you have a much lower iron content, a lower thickness material also starts getting soldering. So the tendency of soldering gets more and more as you reduce the iron content. That is where I was coming from.
Yeah. So I just understood that the metal, I mean, sorry, the iron content is from the aluminum metal what we are injecting into the cavity.
Right.
So we are using ADC 12, sir.
Yeah. There you
So
normally have about 1 to 1.5% iron.
correct, sir. So that is a customer requirement. So we'll just have a deep discussion with this customer also. So what would be the better thing? And as we are also supposed to, I mean, we are trying to get the approval from the customer to have a parting line so that we are wanted to use this conformal type of cooling at the particular area,
Yeah.
which might work. We just wanted to see that if he is not giving the approval, but we wanted to go for any other suggestions, like as you are saying, we have just got from Chemtrend one anti-soil paste.
Yeah.
From that, I wanted to test it on, sir.
Yeah.
So that's what any updates can be done is much okay.
Yeah. Okay.
Fine, sir.
Yeah.
And one more thing, sir. In the short sleeve, sir, our insert materials hardness will be 44 to 46. Based on the condition, we go up to 48. So for short sleeve also, we regularly use the HRC of 48, but here in the presentation, I have seen that it is 55 to 56. Correct, sir?
Yeah. Not only the short sleeve, even the plunger tip, you need to have a much higher hardness. So basically, yeah, go on. Yeah.
So this we are using this hardness can improve this. I mean, life, sir. I mean, at the pouring hole area itself, we are having some erosion. So that's the reason we have gone for some insert type where we can replace that insert, replace that, and keep it on new one. Because the entire short sleeve was okay, only that metal pouring area is getting eroded. That's what I am going for.
Yeah.
For that particular insert, we are using, as you said, 56 HRC. But I'm just asking, so throughout the short sleeve, this 56 HRC can help for the better life.
Yeah. Yeah. Something like scoring and things like that will not happen.
Okay, fine. And okay, sir. Right. Thank you, sir.
Thank you. Should we move forward?
Yes, sir.
Yeah. Thank you. So I'll be going into the existing materials what we use and the kind of methodologies what we have for this particular materials. So as I said earlier, the need for new materials to enhance the thermal conductivity of the die steel, which is insufficient in some of the cases, as I explained. Then the thermal conductivity, improve the mechanical properties with a tight control on the shapes and the contours, and the temperature in of the current and the future applications, as I mentioned earlier. So alternate materials for the components of the die coming in contact with the molten metal, as we discussed now, including the inserts, core pins, plunger tips, chill vents, etc. We'll try to discuss this now. So we have this, if you look at this particular table, we have a type H13 premium, type H13 superior, type 2367 and modified, etc., etc. So if you take the first two, and these are the grades from NATCA, as a metallurgist, looking at this composition, one would not make much difference on the composition between a superior and a premium. Everybody agrees with me? Any questions and doubts on this particular slide?
Sir, which element we need to consider for a better metal, sir? It is silicon or molybdenum? Actually,
If you
the
see,
first,
if you see A and B, I
yeah,
don't see any difference between them.
only the range is increased in A premium in the vanadium 0.8 to 1.2, and whereas it is 0.8 to 1.
I can as well give B instead of A because it is meeting the specification.
Correct. I just wanted to learn about this composition, sir. How to consider for a particular material, so that which chemical composition can impact life or something else like that. So
Yeah.
which should be more or higher or lesser
Yeah.
that
So
can impact the life.
so my take on this is chemical composition. Why chemical composition we are talking about? While we are talking about the chemical composition alone makes no meaning here.
Okay.
So you need to look at how is the steel grade processed, ESR or VAR. People talk about ESR grade steel. I do not know how many know what ESR is and how ESR is used and what is VAR. And at the same time, we need to look at ultrasonic response of this particular material. And I will go into details of each one of this. Why we need to actually look at all these details to get the right kind of a life in the insert. It will be related directly to the insert and the life and the performance of the insert. And you can also look at one of the table below. It talks about microcleanliness in terms of inclusions, types, sulfide, aluminide, silicate, globular, and thin, heavy. These are some of the features one would look at a steel for its performance. So if we have to have a recap on what ESR looks like and what ESR is, I will go through it. Similarly, like a table what I've shown, these are some of the materials, different kinds of materials in the commercial shops, which are available as tool steels. And recently, people started using extensively a steel called Marajin Steel, which is on the lowermost for some of the core pins, and they're also looking at some of the squeeze pins, etc. Again, here, if you look at their materials with ESR, what are the kind of properties? The same material without ESR, what are the kind of properties with the same composition? And why this change in properties? What happens actually? That I will be talking a little more in detail and in depth. So if you look at steel, how steel is manufactured, this is a typical blast furnace. And from the mother earth, we take out steel ore and then start processing through a blast furnace, then a converter and an electric furnace. And these are some of the steel processing. Having processed the steel, this particular steel, after getting alloyed with various alloying elements, is going through a process called slag refining, which is referred to as ESR grade steel. In this, what happens is you have an electrode which is made out of the steel with the composition what I showed earlier. The H13 premium, H13 superior, these are the chemical compositions that are made. And they go through this kind of a process called ESR. The electrode is made with that composition. And this slag is made in such a way that the inclusions in this electrode get dissolved in the slag. So you have a drop by drop, the metal goes into the water cooled copper crucible and gets solidified and forms an ingot. So you basically remove all the inclusions in this process. You homogenize the microstructure of the solidification process, and then so going through this process, basically what happens is you have a limitation on the diameter. The largest diameter ESR furnace in the world today is something like 1.5 meter dia. That is 1500 dia. And you take an ingot out of an ESR furnace, and then you have to go through a VAR, vacuum remelting. This is where you remove the elements like oxygen, carbon, sulfur, all these contaminant elements are removed by vacuum. It is a very high vacuum. It's almost a vacuum of about 10 to the power of minus 6 torr. And this vacuum furnace is again into a copper cooled water crucible. And the diameter of this particular electrode, the limitation would be maximum to 1 meter. So a combination of ESR plus VAR, when a person is able to give a material, the maximum melting diameter of the ingot would be 1 meter. And with this kind of a chemical composition, what we are talking in terms of molybdenum up to 1.75% and vanadium up to 1.2%, the kind of, and chromium with 5%, the kind of density differences that are available when we have a large metal pool which is solidifying slowly here, twice, one in ESR and the second time in VAR, the kind of segregations that happen limits our melting process to maximum to 800 dia, unless lot of innovations in solidification process that have happened, which will add to cost of processing. Why I'm emphasizing on these numbers of 1.5 meters, 1 meter, and 800 dia is, this is the starting point of the steel that is going into our inserts into a die casting die. And this particular steel is forged and supplied to us. So at this stage, when it is forged and supplied, and we are talking in terms of the ultrasonic response of 0.5 millimeters or 1 millimeter flat bottom hole, this actually talks in terms of the kind of a forging that has gone into the material. So all this is important because the material becomes very tough as you go through a ESR or a VAR process, and a lot of forging happens to the material. It is like kneading the dough. The more you knead the dough, the more soft is the roti we have. So it is like kneading the dough. You need to knead the dough properly. You need to see that it doesn't yield, and at the same time have a kind of a toughness. Where we need to go into details in selecting the material, while you look at different H13 grades with ESR and things like that. Now, having gone into ESR, the first time I use the slag is already contaminated with these intermetallics. The second time I use the same slag for the next electrode, the quality of the next ingot is not the same. So the first one could be a superior grade, the second one could be a premium grade. In fact, when I've gone to a few mills, I could see this kind of a segregation based on the number of reuse of this slag. And that is what actually happens when you give different grades of material. And this manifests again in the performance of the insert. Now, having said that, what happens is when we go into forging, I have seen a few of the very well-known tool rooms where they insist on buying the material with the direction of forging that is indicated on the material that is being supplied. This is because what happens is it is something like a plywood, based on the direction of forging, you have these grain orientations that happen. And if you select the direction in which you have a good amicable grain orientation in the direction of your metal flow, the life of the die is much higher. Similarly, I've seen a few tool rooms abroad where they actually polish in the direction of the die orientation when they, forging orientation, when they're actually releasing the die in the last, when they do the final polishing. And this actually introduces some of the compressive stresses. And at the same time, you have the grain orientation in that direction. And then this is how the die life. When we do such kind of practices, there are some tool rooms and some die casting companies which do not use any of the coatings because the control in die manufacturing is so high that we select the material in a right manner. At the same time, we also manufacture the die in a tailored manner based on the application. So this is what I was talking about, residual stresses. Again, these are some of the things which I will not go much into details. This actually impact the die life in terms of heat checks. And these are the mechanisms. And this is how the heat checks and the cracks initiate because of the tensile residual stresses. And this could lead to any of the heat checks and things like that and fatigue crack. So we need to actually control these residual stresses. So we do a lot of heat treatment on these parts and we control the deformation, etc. So I'll not go much into the details of these. Sorry, I don't think we should go into this. So the surface coating, the normal surface coatings are nitriding. It's a gas plasma nitriding that is happening that normally happens with the nitrogen gas with plasma, which actually creates this kind of a few micron thick hardening on the surface of the tool, which reduces the wear and increases the die life. There's one other technology that is being followed. In fact, I was fortunate to have a discussion with Professor George Cross from Colorado School of Mines, where he actually talked about this. A few years ago, they talked about, he's the author of Heat Treatment of Steels. They talked about creating iron oxide on the surface of the die so that it really enhances the die life because it actually entraps some of the lubricants on the die surface and helps in easy uh, ejection of the casting. At the same time, improves the surface hardness of the tool. So this is something people are using silently. Now going into the new materials and technologies. This is one material, a Martin stick stainless steel. It's originally used for the regular razor applications. This is called a razor blade steel. Very high hardness, high wear resistance, and it is normally used for, as I said, cutting applications, shear blades, and things like that. This kind of steel is now getting more and more popular in the die casting area, where we use it at the plunger tip rings and things like that. And these are some of the properties. It's got a good corrosion and wear resistance. And now, based on some of the applications, it is going into some of the areas like the gate area and things like that as inserts. Marajin steel, this was a restricted material for some time, but then now it's becoming more and more popular into the tool area, where it has got a very high strength and high ductility, almost about 1300 to 1800 MPa, proof strength, and good amount of elongation, and very high toughness. It's almost about 95 MPa root meter. And this material is getting more and more popular in the Western world for the applications in ejector pins. So, in fact, some of the ejector pins are as long as the life of the die using this material. And other materials that are coming, the steels that are becoming more and more popular are the niobium microalloy steel, where it gets really good refined grain, so that you have a much higher toughness, and heat checks are much lower here. And nanomaterials are coming in with niobium and carbon and nitrogen intermetallic nanomaterial doped steels are coming. And these are some of the new materials that are coming with different features. In terms of thermal, improving the thermal balance in the die, beryllium copper, which was quite popular, now titanium copper materials are coming, which have been becoming more and more popular these days, which are highly conductive. At the same time, they are mechanically strong. Titanium is very strong, and it could really help in good thermal conductivity, and at the same time look at uh, uh, not getting reacted with aluminum. So we have different kinds of bimetallic materials, diffusion bond materials with steel, again aluminum, steel and copper, and with different kinds of mechanical properties, which are diffusion bond, different processes that are getting into it. And this is something which a lot of innovation that is happening in tool making. And this becomes the USP for any tool maker, where he could offer good amount of life on the tools. So this is something which we captured when we had been to one of the tool room in Europe, and you see a steel core with a copper, contoured copper casing inside, which is diffusion bond to the steel core in the shape of the and there's, in fact, air gap between copper and steel. Actually, it deteriorates the insert more than having a copper insert here. So there should not be any air gap. So it is a diffusion bond copper into steel insert, very complex one. And you have a jet cooling, which actually, it almost goes to the surface of the steel, the copper. So even though there's a cracking on the steel's insert surface, there's no water leakage. So these are some of the things which are quite innovative, and people have been incorporating in some of their designs with multi-material, multi-processed design. That is a dissection of that particular assembly. So you have the contour of the copper, which has gone exactly into this kind of insert. And in fact, it can go as close to the surface as possible. Again, embedded cooling, the refrigerator type, and you have different kinds of materials that go into it. And you could also look at ceramics, where you need a little bit of insulation in the tool. A lot of ceramics being used into permanent mold tools, so that you could actually have insulation there, along with some of the cooling arrangements. Now, going to coating, you have different kinds of physical vapor deposition coatings, plasma aided, plasma unaided. You have a nitrated layer, which is done with different metals, titanium, chromium, and titanium carbide, kind of a nitrated coatings, which actually have different levels of thickness of the inserts. And at the same time, you have different kinds of hardness that can be developed on the tool surface. So these are some of the examples where you have different levels of soldering, what you were talking about on the core pins, where we could reduce the soldering by nitriding operation with either titanium aluminum nitride or chromium nitride, or a simple nitriding based on the requirements of the design. So you have different kinds of processes, the kind of life these coatings can improve on the substrate of the insert or the core pins. Thank you. Any questions? It's a very vast subject. In fact, 1.5 hours is really a short time to actually spend on this, but then it's a kind of
Dr. Rao, that was an excellent, excellent presentation. You had almost completed a one full subject in an hour and a half. It's like 1 year, one semester, one topic, one subject in an hour and a half. It's really tough, and tough to lecture as well as difficult to understand also. So I request all the those who present, ladies and gentlemen, if you have any questions, you can put it in the chat box, or you can also write directly to ALUCAST. We will try to get some reply from Dr. Rao and then email it to you. In the meanwhile, there is one question.
Yeah.
Rushikesh, can you switch on Praveen, his mic, so that he can ask the question directly?
Whose mic, sir?
Praveen. Okay, I'll read out the question. Need to elaborate about the core pin material.
Sorry.
Good afternoon, sir.
Good afternoon.
You're back. Okay.
Sir, which process, plasma nitriding or gas nitriding, is better for surface finish?
Are you talking about surface finish, or you're talking about
Due to heat check marks.
Yeah, heat check marks. See, I did not touch upon one more topic, that is rockenizing.
Okay.
So for heat check marks, actually what I would go in for is a process called rockenizing. It is something to do with friction stir welding. So you have a hard material like molybdenum or tungsten or vanadium based electrode, which is actually you have a few micron deposition through friction stir welding onto the substrate. So this would actually help in repair of these heat check marks. If you really talk in terms of retarding the heat check marks for a new die, then I would actually go in for something like titanium nitriding or titanium carbonitriding process of physical vapor deposition, PVD.
Okay, sir. Thank you.
Yeah, thank you.
Dr. Rao, there is a question from Mr. Mahesh in the chat box. Can you ask one in the chat box?
It's in the chat box?
Yeah, you can open chat box on the right side in Zoom.
Yeah.
Or,
Good evening, sir.
Yeah.
Good evening. This is Maheshwar from Rico Auto Industries.
Yeah, Mahesh, you can go ahead and ask the question directly.
So, in aluminum die casting, I'm discussing about this. One component is having heavy wall thickness.
Yeah.
Here I cannot provide cooling. So, which kind of material I can choose for that?
Yeah, that is what I was trying to say. When you have very high thickness, I didn't go into specifics here. When you have very high thickness, you can actually go enhance the cooling there.
No, sir. Where I cannot provide cooling in that area. So I can choose a particular material for this. So insert material or punch material, something like that.
Yeah, you need to go in for a much higher thermal conductivity material, something like anvil alloy there, and then try to pull out that heat from a different location from that particular material. So you need to connect the dots there. So you have a thick mass somewhere internal. So
yes,
you need to actually have an insert of a different material with a high thermal conductivity there. And then to that material, you add some other material with a higher thermal conductivity through which you have a cooling arrangement. So you need to connect this as a train. So basically you need to pull out that heat from there.
Yes, sir.
Yeah.
Is there any other question? Gentlemen?
Sir, can you please elaborate how this, while we put this copper cartridge cooling, water would more damage die steel?
Yeah, I'll just try to see if I can put a pointer here. Yeah. So you have this copper here, which is going only up to this particular surface. What happens is if I increase this copper thickness much higher and reduce this steel thickness here. So my water is not going up to the end of the copper here. So my water flow will be much lower. I increase this thickness of copper and reduce the thickness of steel here. So I can play around. So even though I have about 2 or 3 millimeters or 5 millimeters of insert thickness, I'm still pulling out the heat from here. And having this copper shield, if there's any crack here, nothing happens because water is not going in there. And copper will never crack. It has got very high ductility. Did I answer you?
Yes, sir. Yes, sir. Thank you. Sir, can you also elaborate on cladded cooling system and nozzle coolings?
Yeah, see, uh, uh, cladded, actually you can use a nozzle cooling here. Even here you can use what happens is when you have this this is cladded. This is a copper cladding here. If I have a solid copper here, actually copper actually removes the heat from here and it conducts. But end of the other end, copper doesn't know where to throw that heat out. So it has to conduct it out. So it has to throw that heat out. So that is how you use a water cooling there. And then you can use a nozzle or you can use a jet cooling there or a continuous cooling. But normally when you use copper, you go in for a jet cooling or a nozzle cooling. Yeah.
We
Thank you,
have
sir.
still some more time for taking a couple of more questions.
Yeah, sure.
Okay, from my side, Dr. Rao, I have a small request to you.
Yeah.
This presentation, what you gave is very interesting and highly informative. So I would request you if you can put it in the form of a small article, whatever you can share. I will publish it in our journal so that the reach will be much more.
Okay, sure.
Many people may not be able to.
Unfortunately, I'm not getting the time to write it. I'll have one of my engineers put it down so that both of us will publish it together.
Yeah, please do that. That will be extremely good. And send it across. With of course, we'll put it with your name and photo, so that people will can have a better reach. That's one.
Yeah. Thank you.
Gentlemen, any questions?
Yes, sir. Sir, can you name 3 methods how to improve the die life? Die life in HPDC casting.
Yeah, one is you should have a robust system of stress relieving. See, what happens is the die is actually having a cyclic heating and cooling cycle. And you have a lot of residual stresses built into the die. So the inserts need to be periodically stress relieved based on the configuration of the part that you are producing and the volume of those parts that you are producing. That is one thing that is a low hanging fruit, which is a normally established process. The second thing is we need to see that we have a lot of internal cooling rather than a spray cooling. While we look at using spray basically only for lubrication and the kind of non-sticking requirement of the part to the die. So to that extent, if we use the spray and not use excess spray for cooling the die and have a lot of internal cooling, that really helps in extending the life. Then the third thing is we need to see that the die does not look at too high temperature and low temperature in each cycle. So the thermal fatigue is removed. So the heat checks are reduced and the die life improves. So basically we need to look at having the spray or the die loops which can be stable at a higher temperature and operate the die at a high temperature. To my knowledge, I think these are the three things. If we could really follow with rigor, we should be able to have, at least this is what I see from some of the foundries which are good, which have got very good die life. Yeah.
I fully agree with Dr. Rao.
Good afternoon, sir.
Yeah, just a second. To add a point, the heating and cooling system in the die should be extremely good. And die lubricant should be diluted to the minimum extent possible and used very limited quantity. So the heating and cooling unit is extremely good. Heating and cooling system attached to the die, then your die life will greatly improve. Yes, please. Next question.
Good afternoon, doctor. This is Padma Narayanan.
Yeah.
I request you to develop on this impurities on the die inserts, which what are all the areas it affects the die cycle, total life cycle?
Yeah. Actually, that's a very good question. In fact, this is something, it's very close to my heart. See, what happens is these inclusions, these are called inclusions. These are inclusions of sulfides, which are normally available in any of the steels. I'll give a small example. We are using this cutlery every day in and day out. We are using this cutlery in the kitchen. This cutlery is supposed to be the most purest steel, wherein it is always sharp. Whatever you try to uh, uh, cut and things like that, for that kind of weight of that steel, we are paying quite a bit. And because the steel that goes into it is very pure, it goes through a lot of in fact, another, I gave an example of razor blade steel, what we use for shaving. This is again a very highly pure steel, where the inclusions, now I'm coming to the inclusions, these inclusions actually create that kind of they just come out of the steel when you have a lot of mechanical loading. And this kind of chip off, you can call micro level chip off of these inclusions from the steel surface, actually initiates this kind of heat check marks. So whether it is calcium based or silicon based or sulfur based or phosphorus based, these are the impurities that come into the steel right from the time it is mined from the Mother Earth. So that is why people go into this electro slag refining, where the slag is made, it is like a sink. So it actually attracts like a magnet all these inclusions into the slag. And drop by drop, when the metal, that is the steel, that is melted and goes through the slag, the magnetic attraction of these inclusions into the slag makes the metal clean. Did I answer the question?
Yeah. Thank you, doctor. And then the same question for exactly the sulfur. When people say the sulfur, even if it is present with my micro traces, it affects the die life. It creates the early heat check marks.
Yes.
How to view on that, doctor?
Yeah, actually sulfur, what happens is sulfur actually goes to the grain boundaries and it weakens the grain boundaries. That is where you find those zigzag heat checks. They actually go along the grain boundaries. So these zigzag heat checks, normally it is controlled by through the ESR process, again by alloying elements. If you see, you should always buy a material with high manganese there. Manganese should be on a higher side. So sulfur is something which gets scavenged out by manganese.
Okay.
So this is what happens. So when you're selecting a material, you should see that manganese is on the higher side of the band of your specification.
The continuation of the same question, even though we buy the correct material from the supplier as per our specification, but how to ensure that the heat treatment and other cycles are followed through, because it is not only the design and material selection, and then vacuum heat treatment also plays a vital role. How do we select in the process?
Absolutely. So what happens is normally in some of the good tool making companies, what they do is when the insert is going for heat treatment, along with the insert, you have a test bar that is actually tied up with the insert from the same material, goes along with the insert, it undergoes heat treatment, comes out. After it comes out from the heat treatment, again, this coupon of the test bar should be of a thickness, maximum thickness of the insert. So once you take this coupon, you do a lot of metallurgical evaluation of it, right from hardness, tensile strength, microstructure. And when you talk about microstructure, you look at inclusions also, what I said, A, B, C, D, thick
Yeah,
and thin.
okay. Okay.
Then once you get this test report and you have a specification fixed, automatically the heat treatment should have been done properly.
Okay. Thank you, doctor.
Thank you.
Sir, hello.
Yeah.
Sir, Giri speaking, sir, from Rane.
Yeah.
Sir, actually, for the core pins, after certain life, the nitrogen layer will go off and its life will be gone. Based on our experience, we will change the pins. So, in the same way, for the insets, we are sending outside for the stress relieving process after certain shots. But the nitrating layer, which was first initiated, will be gone after few shots. Do you recommend after certain shots again polishing and nitrating will help, or it may not, or it will deform or it will develop the internal stresses again?
No, you can actually, what happens is, what you said is right. After stress relieving, if you do polishing, actually polishing will induce compressive stress. Under compressive stresses, you will not have any kind of a heat check marks. Heat check marks form only when you have tensile stresses in the system. So when you do a polishing properly, you induce compressive stresses on the insert after good stress relieving activity. Your life of the insert should improve. On top of it, if you do something like a nitrating operation, it should enhance it further.
Sir, how would polishing give this tensile stresses, sir? Is there any, by any chance, would polishing lead to tensile stresses?
No, polishing will always induce compressive stresses on the surface. If you do grinding, grinding gives tensile stresses. So because grinding actually enhances the tensile stresses because there'll be micro cracks there. Grinding or even EDM gives you micro cracks.
Gentlemen, thank you very much, all of you, for patiently participating in this event. Once again, I record my appreciation to Dr. Rao for giving us a very excellent, informative paper and a good presentation.
Thank you, Ganeshan.
Yeah, thank you and see you all. We are conducting a series of ALUCAST training program. This is first of the 4 or 5 on die steel or die portion, which is undertaken by ALUCAST Chennai chapter under Mr. Prabhakaran. So we will have this type of events at least once in a month for the next 3-4 months. We request all of you to pre-register and we will try to put it in the convenient time so that more and more people can participate. Thank you. And thank you, Mr. Dr. Rao. Thank you.
Thank you, Ganeshan. Thank you very much. Thank you.